All right. Um, good. Let's just get started. Hello, everybody, and welcome back to the IBM. Well, this case it will be tutorial, actually, not seminar, but the IBM seminar / tutorial. And today we are fortunate to actually invite over Song Han from Northwestern University now, former UCSB, now Northwestern, where she just started her what should we call it, new laboratory in the well in the prominent field. Now, Songy is obviously well known for all her discoveries and um, progress she has made, and specifically actually towards the DNP. And for that reason, we decided to actually invite over, or actually Songy offered to come over and present specifically on the Oberhauser DNP and how we can utilize it to understand the dynamic of water or the localization of water in biomolecules. And for that, I'm just going to give over the stage to Songy, and I think you can take it from here.
Thank you, Thomas. Thank you for inviting me. And, we talked a lot before what I think you'd like to achieve. So hopefully I will do some of that, or hopefully it'll be useful. So I decided to start with the EPS Society a little bit. I am currently the president of the EPS Society. There'll be an election at the end of the year. So we have amazing, wonderful candidates lined up. But I really would like to answer this question. Why do we need to be part of a scientific society, especially for students and postdoc, and also faculty, in case it's not clear? It's because science is done in teams. Science requires people, not just because you need group members, not just because you need advisors, but also because who is going to review your paper? Who is going to review your grants? This is significant work. And so it took me a while to understand that. So a scientific society is there to facilitate and translate, because different communities have different people. It's not that everyone can be clearly well known to the entire scientific community. So the specific scientific communities are there for the people to really elevate students, postdoc, and faculty, highlight them. And very importantly, it has to be a dynamic society. So Thomas Prisner and I, we were each president for each 3 years, almost, my term is almost done. We tried very hard to change. We did successfully, but the change has to continue, right? It's not static. There's so much work to be done. So the reason I would like everyone to consider to be really an active part of the society is because that really elevates your academic success, your academic prospects for both students and postdocs, and also future, those who go to industry. You need to come back to the society and they will be trusting you with the products, right? So we have 3 forums. One is the Twitter. A few people helping here and really grateful for that. But even the Twitter, I guess I should say X, activity isn't perfect. We need even more people. I am very aware of it, but we are doing currently what we can. Anybody who is interested, trust me, there's work to do. By the way, a virtual media team will be a much more official part of the next IES executive committee. So stay tuned. And if interested, I always have found a way so far to involve people when they asked. The other forum is, of course, this virtual EPR meeting. Thank you, Thomas, and all the committee members. This is so important and so impressive. So I just stole one of your slides to show this. Wonderful work. And I think you have a YouTube channel, correct, Thomas? IVM YouTube channel. Okay. The third forum is the EPR newsletter. We have a dedicated chief editor, Laila Mosina. She really is about people. She's amazing. She will talk to you, interview you. The whole point and the goal of hers will be, how can we highlight you? And you means students, undergraduate, PhD student, faculty, anybody who is interested in. And one way to get into the newsletter is to give a talk at the IVM or get a prize and certain activities. And then we are here to feature you. So hopefully that convinces you to be a very active part of EPR society and help us grow. And the scope is still narrow, actually. Now, what I mean by that is the society is still small. We could become bigger. That is a good thing. So something to think about. Okay. So I changed my title just a little bit. I decided to call it DNP to enhance the detection of wet interface interaction. And since Thomas told me something about, we would like you to give a presentation and maybe set the stage. And I said, set the stage. What does that mean actually? So I decided to just share just a few thoughts about presentation and what I experienced in UCSB. I was there 19 years, absolutely amazing time, and not moving because anything is wrong with UCSB, but because I had new opportunities, okay? But UCSB taught me a lot, and I would like to say a couple of things will be obvious to you, but I'll explain why it's not so obvious. So I decided to start a tutorial with a motivation, not with the lecture material, because maybe not in the IVM, but typically a half the audience or less if you're lucky or more, a zone off. And it's often because they don't understand why they should care, or because they just get lost very easily. And it has a lot to do with details. And I remember I thought I gave a talk, I thought I made it so clear. And then I got not frustrated, but more like puzzled that a lot of my colleagues, most of them are non-magnetic resonance, still would tell me, there's a lot of detail. I lost you. It sounded cool, but I didn't get it. And I thought I explained it. And so I realized there is no such thing as too clear. You have to make it clearer and even clearer. And that's because people from different disciplines actually think differently and have different language. And so this is really to be taken very seriously. And of course, I'm still learning in progress. But the other important part is when I say motivation or even big picture, it doesn't mean application. It doesn't mean that your work has to connect to sustainable energy or medicine, actually. It can be absolutely fundamental science that has no apparent connection to utility, but you still need to justify, why should I study this fundamental phenomenon? Because there are 1,000 phenomena, maybe 1,000,000 phenomena. Why should I study this phenomenon, not this other phenomena, right? So even for fundamental research, we need to explain, why did I decide to use my valuable time on this topic? So I know it's somewhat obvious, but I think I would like you students to think about that, and happy to talk more about it if you have questions. But there's a conundrum. And I see this conundrum actually quite a bit, that sometimes it isn't juggled well, especially in job talks, but also sometimes in PhD students when they give talks at conferences. So let's just take a conference. And I'm not talking about magnetic resonance conference. I'm talking about the APS March meeting or ACS meeting, right? You talk about your project. Let's say it's about liquid phase separation or whatever it is, biochemistry. What often the students don't consider is the conundrum of expertise, right? When we motivate work, it's not just there's this very important problem and therefore I'm going to tackle that. Let's say we need better energy sources. That is not the only aspect, because there's so much to do that we must consider expertise. I think this is what I see a lot, that you have to satisfy the question, why does it need to be you? Especially if it's an obvious big question, medicine, energy. There are 1,000 people who could be doing the work. Why are you doing the work? And that is, of course, because you have specific expertise. And that's also the joy and the conundrum of a PhD, that you need to become an expert in something. And yeah, I hope I made it clear that it's a conundrum, because it's sort of a duality, right? You explain what's an important problem, but you also have to explain what your expertise is and connect the dots why we need to solve this problem with these tools. And you are somewhat, of course, constrained by your tool, and that's okay. Maybe there are questions about this one. I don't know, because it should be open. If you have, let me know, because we are going to switch now to science. If not, hold your question, and then if you have in between, you can raise your hand. Okay, so in the spirit of that, we need to still stay, of course, within our expertise, because that's how we can make the biggest impact, by being experts. Let's think about magnetic resonance. And I will say something obvious, but I would like to emphasize that the spins of nuclei and electrons are incredibly sensitive and incredibly precise probes of the environment, even more than you think. You all know MRI, you know, chemistry, structure, and we all know that. But there is so much more. The topic that I will be talking about today is water on the surface of proteins or polymers or surfaces. And it turns out that we can study the dynamics and structure in detail. It has to be combined with computational work using NMR much beyond what was considered possible. And that principle is true for so many other things, because if you think about it, you have a protein system, a material system, and you'd like to understand the detailed chemistry, the detailed coordination, or the dynamics of your spins. Tell me whether there is a much better method to do that than spins. You will be hard-pressed to come up with that. Optical methods are amazing because, of course, there is sensitivity. But I don't need to tell you, and I will tell that happily to my optical colleagues as well. Of course, each spectroscopy has its place, but I think it's important that NMR and EPR young scientists are very proud of that field, because the growth potential is infinite. There's so much chemistry, dynamics, and structure that NMR and EPR can resolve that no other technique can do. We are just beginning to scratch the surface. But I think what's important is that we very carefully explain that, because if you just say NMR spectroscopy, then people think of, oh, the thing where, you know, organic chemistry, 1D, and people know NMR from different angles, and therefore one really need to take time and explain what is the strength of spins as your tool. Okay, that's enough of that. So now, as I said, I would like to talk about water structure. And I use the word structure on purpose. And that's because even though today's talk will be about measuring dynamics, you will see that why is dynamics important? Well, you can think of kinetics and thermodynamics, okay? And I'll tell you already, what we measure is thermodynamics, not kinetics. And why is it important? It's because it can predict thermodynamical binding property of function, okay? And the connection is through structure. It will become clear. I have two ways to motivate why should we study water structure and dynamics near surfaces. I think there are so many examples where water structure is important, but let me just mention two types of, like, one more overarching and the other one in more detail. I think, okay. So generally in protein, so don't worry about the small legends or words. We all know that resolution revolution really is continuing and has transformed the scientific field, right? We also know that cryo-EM made a huge difference, at least for certain categories of protein, to really get at the structure. And I know that some of our NMR, maybe students might be feeling cryo-EM is threatening the magnetic resonance community. Absolutely not, because it's, in my opinion, a blessing, because then they can measure the structure much faster, at least to some extent, so that NMR can do the much more interesting work, such as dynamics and functional property. But anyhow, let's say you have a structure with the best resolution, let's just say X-ray crystallography. One still doesn't know, typically at least, how to translate that surface topology and structure into function. Okay, yes, alpha fold, you can fold something, but predicting active site or predicting binding site only with a priori knowledge, not upfront, meaning there's a translation missing. It's there, nature knows it, but how does nature know that this is the active site, not this one? So we can make a guess that at least half of the answer lies in the water structure. Why? Because if you take just binding as your canonical function, let's just say, for the sake of argument, about half of that energy is solvation energy, solvation entropy, solvation enthalpy of both the ligand and the protein, okay? So at least half of the answer is water, just by definition. And of course, there is, once the approach has happened, in detail, there is chemistry, there's electrostatic, and there's all sorts of other interaction. But initially, water is just playing a huge role. There's no way around it, okay? So that was general. And when I say active site, let me give you one example where water could be specifically playing a role. And I know that the next one is maybe somewhat of an obnoxious cartoon. It's good looking. It could be obnoxious because it's not real, of course, but it hopefully serves the purpose of what I'm trying to say. So the so-called active site could be anywhere, could be on a protein, could be on a catalyst, nanoparticle. The rest of the surface could be your more inert silica surface, or it could be a protein surface. Very often, active sites have been postulated to have a certain feature, or at least active site operating underwater. It's very different. If it's not water, it's a different thing. But if active sites are underwater, it has been postulated for a long time, but rarely measured, that you have this block that I just say active site that does the catalysis, that is protected or hydrated by this wrap water or clatrate-like water. A real clatrate completely encompasses methane, for example, and a half clatrate is a situation when the inner active site is of a chemical nature where water can't directly hydrogen bond. But as long as this entity is less than a nanometer, it's free energetically better for water to anchor down around it and then form hydrogen bonding bridges around it, like two-dimensional. It's enthalpically not as strong as properly hydrogen bonding down to the surface, but there's a balance. There's a balance. That's actually not true. What I just said is a little bit wrong. The hydrogen bond strength of the 2D tent is actually stronger. Apology. It compensates for that. But overall, free energetically, the penalty you pay with this low entropy water, because it's more ordered, it's more tetrahedral, the angles are different, is worth it. Okay. Overall, free energetically. This water has really special and very general property, namely, when a ligand comes or another protein comes, this is the water that can much more easily get evicted compared to the hydrogen bonding network that's contiguously hydrating a surface. Why that is, we can talk more about it if that's unclear, but this low entropy water is considered to be easily evictable. So when a ligand comes and you evict water that's ordered, then you're gaining entropy because of that. Also, you're guiding the ligand towards the active site without the ligand having to do a complete search, right? And then the ligand can then, due to specific chemistry, bind and do its chemistry. So if that's the goal, what would we like to measure? We would like to measure structure of water ideally and dynamics. So, and I started my talk by saying magnetic resonance is actually amazing. There is not infinite, maybe it's not so strong a word. There's so much future in both NMR and EPR, but I think we as a community need to really work on communicating that excitement and not ourselves get into a certain way of thinking about and talking about NMR. And if needed, invent new words. That's fine. Other communities do that too. We can talk about word choices too, like quantum sensing, okay? If needed, we can invent words too to make it appealing. But anyhow, NMR got it all. So structure can be measured by oxygen-17 chemical shift, or at least is a very, very good readout. This, of course, has been known for a long time, especially in the oxide community and glass and crystal. But only more recently, beautiful work by Tim Cross and also Bob Griffin and many others have rediscovered, if you will, or kind of elevated oxygen-17. I also recently got really interested in this because it turns out it is even very successful in solution state. So I'll not be talking about this, but I will tell you that we have tested many systems where the chemical shift is a really good readout for structural property. You might say then, it's just a shift. Yes, it's just a shift. As in other spectroscopies too, if you think about terahertz, neutron scattering, IR, it always has to be combined with computational method, because experimental method is naturally lower dimensional, in this case, chemical shift, let's just say. But that gives a very powerful readout to test, and the rest of the blank can be filled out by computational work. So we got structure on the one hand and dynamics on the other hand through Overhauser DNP. That's, of course, going to be my main topic, okay? So having this duality is super helpful. Now about dynamics. How does it work? Well, let's think about what kind of dynamics we are interested in. Ideally, we are interested in a whole scale of dynamics, because the time scale is interesting all the way from picosecond to nanosecond. So picosecond dynamic is when you're talking about water rotating, what do you need? You need to break actually all hydrogen bonds and at least rotate, right? But we are talking about one water rotation is something like a rotation correlation time of some between 10 and 20 picosecond. Would be really cool to measure that, right? There's, of course, librational dynamics, that's even faster. And then there's translation, which is breaking hydrogen bond, changing position. Another water has to break hydrogen bond. So translation is quite a bit more musical chair than rotation. And that correlation time is something of the order of 30 to 50 picosecond in bulk-like water. And then there's a whole gamut of dynamics if it's on a surface of proteins and other things, okay? It just happened to be so that the electron spin that 20 years ago when I started was easy to just get some EPI and DNP was at X-band. So 10 gigahertz is the electron Lamarck frequency. And it happened to be just a really good dynamics to read out dynamics in the tens of picosecond to about nanosecond, okay? So that's why we settled on this field and are measuring translational dynamics, and I'll tell you about it. And it turns out I got very lucky that this tens of picosecond and hundreds of picosecond really tells us about the structural topology and is a proxy for structure. I could have gotten also much less lucky, right? So this was definitely serendipitous. Now, if I had a magic wand, I would like to measure this at many fields. Let me go here. So typical Overhauser DNP system used for water dynamics, and there are several groups here. Of course, John Frank and also Bridge 12, and I'm sure I'm missing now a lot of people, I'm blanking, a lot of people. But not still, we can count as not that many, is because that X-band is still not trivial. And the reason why it's not trivial is you're trying to microwave a sample and without heating it. So that's actually the major challenge. Now, if technology was more advanced and there was a way to do it, especially cavities that can be tunable, if I could do Overhauser DNP at 3 gigahertz, 5 gigahertz, 7 gigahertz, 10 gigahertz, a whole range, it'd be amazing. Okay, we can get a whole range of dynamics. So it really is the technology, the cavity, the source, controlling the saturation factor, which makes it non-trivial. Many years ago, I think John, Frank, and I tried, and a couple other students tried, but we paused it. I don't want to say give up on it, just because it's just a lot of work, and we had PhDs to defend and jobs to get stuck on it. But technology is always advancing, right? So I think this slide really doesn't have any particular information. I'll just say one thing about this. I'll explain it on the next slide, and I'll use a cartoon version first before I get to the physics of it. So the way it works is that you have a magnetic field, your electron spin Larmor frequency. And now the proton nuclear spin is moving in the sphere somewhere around the electron spin. And the frequency, Larmor frequency between the two are completely 3 orders of magnitude, well, almost 3 orders of magnitude different. They shouldn't couple except when movement, basically the time or the speed at which the proton traverses the near field of the electron spin, is of the order of the period of the electron Larmor frequency. Okay, it's really like the Doppler effect. That's how I would like to think about it. You have to be fast enough, like the train, to see something. When now and I flip an electron spin, I can't see that unless I'm running with the train. So electron spin is doing this, and I need protons that are moving somewhere of fast enough or close enough to that frequency to be actually even detectable. And now when I flip electron spin up or down, the nuclear spin couple, and I can see, I can then energetically also flip-flop a proton spin. So that cartoon, many of you have seen it many times, but I just like showing that because it's, I guess slides are not showing in that exact order. I was just thinking. Let me just do a quick detour on this one. The only thing I want to say about that is DNP. I think all of you know DNP, of course. We are all fans. I'm just mentioning here 4 major categories of DNP: Overhauser effect, solid effect, thermal mixing effect, cross effect, right? What I wanted to say is, among these, only one is a driven process, solid effect. Only one is where you use photons to do something about the transfer. Only one is controlled by a human, if you will, or technology, solid effect. Overhauser effect, cross effect, thermal mixing, the sample does the job. The sample has to match energy, frequency, any condition. And then we can interfere by controlling saturation. We are not controlling the property. But you can turn it around and say, exactly that's why we can learn something about the sample from Overhauser effect, cross effect, and thermal mixing effect, okay? We are, of course, not going to talk about cross effect and thermal mixing effect, but just keep that in mind. These 3 effects are basically relaxation-based effect. In the sense, they're spontaneous flip-flop. So I'm learning something about the flip-flop, and from there I can glean something about the property. And the set DNP is just a means to read out what's going on in the sample, unlike the solid effect that I'm driving, right? Okay. So the next cartoon is something I believe many of you have seen, but maybe some of you haven't seen, and I keep using this cartoon because I think it's illustrative. So we have an electron spin, typically in the form of nitroxide. I sometimes wonder what would happen if we didn't have nitroxide. It's such an important radical because Overhauser DNP does work without a radical, but not as efficiently. I mean, nitroxide is really kind of the magic middle ground. You know, there's a radical is somewhere between the nitrogen and the oxygen, is exposed enough to read water nearby, unlike tridal, where the water is a little too far away, but protected enough with the methyl or some other groups to not be degraded, and small enough and not hydrophobic or charged that typically it is much less perturbing than you might think. I'll get to that perturbation in a second, in a little bit, but let's first see how it works. So you have your electron spin doing its precession, and in order to have a actually electron spin flip-flop, you could of course have your thermal fluctuation, but I could be driving that transition too. And as I said, I need protons moving fast enough. And if the scale matches, then I can have a flip. And the nuclear spin T1 is long enough that once it flipped, it will live forever. So why do I get actually enhancement? So this process is going on no matter what you do anyway in the background. It's just that electron spins are higher polarized than proton spin. So when I now saturate, there's a certain preference whether I do flip-flop or flop-flip. And because of that preference, due to the original polarization of the electron spin that's higher, about 658 times higher, I can get proton enhancement up to about half of that. Why half? If you have dipolar coupling. If you have scalar coupling, it's a different physics. And there you can get a higher enhancement, but then also you depend on many other properties of the sample. So let's strictly keep with dipolar through space. I'm not talking about any orbital overlap. Then the maximum enhancement is about 300, I get 300 something, right? Okay, so now what am I gonna get out of this information? So as I said, it's just a probe to read out what's going on in the background, and now I have to skip through this animation. And this is a imagery that comes from John Frank. Actually, I'm borrowing it a lot because I so far is a really good illustration in my opinion. So your electric EPR spin is like your field, and a proton is zipping around it, right? When coupling happens, indeed, what the proton sees is a spin, so magnetic property, right? So you flip, and then you have a concurrent or subsequent flip-flop. So I can, by molecular dynamic simulation, obtain something like a dipolar time correlation function if I could track these two particles computationally. So it would, and in fact, that's what ultimately I started this collaboration a long time ago with actually Shihan Ham. She sadly passed away. And so we had like a break of 5 years, and we rekindled it with Professor Scott Schell and his student Dennis Robinson. He did an amazing job, and that paper is currently in submitted. And anyway, the dipolar time correlation function is microscopically what's going on. And if you could measure that, a Fourier transform of it will give you the spectral density function, okay? And then you can get at the NMR frequency or at the EPR frequency, 10 gigahertz or 15 megahertz, the amplitude of the spectral density function, J of omega, and you could obtain properties about dynamics. It's just that we cannot measure dipolar time correlation function experimentally by NMR, right? What do we measure? We measure enhancement. We measure T1 with the radical, T1 without the radical, and then the saturation factor, right? So our main observable is the enhancement. So we are using enhancement as a tool. And the equation here is just really making assumptions that it's purely dipolar. And there's even, well, that's the only assumption, actually. The only assumption is one electron, one nucleus in dipolar, okay? So this equation really is well established. But I want to point out a few things. So in that equation, you see W2 minus W0. This is the basically relaxivity at the EPR frequency, because it's the double and zero quantum transition. And though you would know, even in solid state DNP is the same way. If you want enhancement, you need one or the other transition to dominate. The same here. So W2 minus W0 needs to be not zero, which is the case in this, if there's coupling. And then you have in the denominator, this entire term is basically a 1 over T1 that you can measure. This W superscript 0 is a 1 over T1 that you would measure without the radical, meaning all the other relaxation mechanism due to phonons and other nuclear spin. And then the W2, W02, W1, all of these contribute to also relaxation, right? Because if you do flip-flop, double quantum or zero quantum, or even one electron spin flip-flop, think of PRE, all of those are also relaxation mechanism, right? So I measure enhancement, T1, T1, 0, and I can extract, in principle, interesting quantities. So what are the interesting, interesting quantity. I'll get there in the next slide. Practically speaking, in the early years, the saturation factor tripped us for many years. In fact, one of our first two papers, when we were talking about using ODNP for water, was on understanding saturation. That's intricate, actually. You have 3 nitrogen lines, right? You need either no exchange or full exchange. Anything in between is complicated. And in fact, Marina Benati's group did beautiful work back then. That's how we met. We were battling a little bit, but it was friendly battle, and we are very good friends now. Back then I didn't know her, but this is how this whole the interaction started. The saturation factor, it's pretty complicated. So if you have a very good Eldor setup, you can measure it. It's not trivial. I really think even today, the saturation factor is technically the more difficult aspect of ODNP measurement. If I could just measure that reliably, the rest of the measurement would be easy. So sample heating control and saturation is the biggest problem, okay? The rest we can solve, but of course, we got it under control at X-band. Doesn't mean that it's easily transferable to other frequencies, as I mentioned. So with that, then we can get quantities of interest. One is what is known as the coupling factor. You see it's a ratio between W2 minus W0 and these other terms. What is important, so this kind of physics, how do we calculate that, is both published in a progress paper that John Frank is the first author of, and there will be a paper coming up hopefully in a month or so that reiterate some of that from the computational side, so you can look it up, but it's a straightforward derivation. What is important is that we recognize in the denominator, we have NMR and EPR frequencies. So there is dynamics on both scales contributing to the coupling factor, and the fast time scale in the denominator, okay? The other aspect is why coupling factor tend to be still easier to handle than these terms separately is because it's a ratio. A lot of these nasty cofactors cancel out. That's why if we could do Overhauser DNP reliably, even at 2 different frequencies, that could be even very close. We tried that, and even there, at some point, we run out of time. Let's say 8 gigahertz and 9 gigahertz. You could measure ratios, and that would be amazing. So one day, somebody will do it. I might do it. We'll see. Okay, but right now we don't have that. But really, there are scenarios where we really need to know, is it a picosecond dynamics or is it a nanosecond dynamics? So we have good reasons to wanting a relaxivity proportional to the W2 minus W0 term, which is only containing the EPR frequency and the slow term, okay? So we can do that. And I'm actually realizing, Thomas, see, whenever other people go over time, it's like long. When I talk, I think I just talked a little bit, and now the time is already 45. So what do? I have,
why don't we continue a little bit more?
Huh?
Why don't we continue a little bit more?
Yeah, let me try that. Yeah, because I do need to get to the structure, and I need to show you kind of a conundrum. Let me try like no more than 10 minutes, okay? And then, okay, let me skip that over, and let me skip this over. So you got the point about the, okay, the important point is this. There's coupling factor. It's a practical choice. The fast relaxivity is important to differentiate from slow relaxivity. And those who know the history of NMR studying water would know that the bound water is what tripped the community something like 40 years ago when people were trying to use NMR relaxivity to get dynamics. This slow water was the problem. That one messed everything up because this is a very big effect. And then you never know, is it a fast, is it a slow? So the principle of ODNP getting at dynamic is really the same principle as NMR relaxometry. It's the same principle. The only difference is because we have this electron spin, you can separate out the time scale that we want and separate out terms in a way that's harder if you have just nuclear spin and a range of fields, right? Okay, so I tell this story a lot, but let me just say that again. When we started, because we are measuring dynamics, I thought we are going to use it as a tool to track protein folding and protein aggregation. Because when a water is exposed versus buried, the dynamics would be different. And that is true. One of the first papers was a folding paper, together with, by the way, Silvia Cavaniero and Wayne Hubble. But what turns out to be even more interesting is the surface having variation when there's no obvious difference in confinement. Let me qualify that. Later we learned that little topological differences like concavity and convexity plays a big role. So that's half of it. So yes, that's still, if you will, structure. But then there is an effect, which is really chemistry. So even when we talk about structure, let me give you, this is the story I really want to briefly tell you. I'm just going to talk about glycerol, believe it or not. And I'll show you one version of the story where you will think, oh, they understood everything. And I'll tell you at the end one slide where I show you why this is not the case. So this paper is also currently submitted, right? Also a story that has been going on for 5 years. Basically, we took water glycerol from 0 to 100. There are a few solvents where you can do something like that. Glycerol, DMSO, so we are studying them all. And put a little bit of spin labels in there and then vary the whole range. So you see the spectral density function here computed. You see that it varies with glycerol concentration. And then superficially, you see the ODNP-derived coupling factor and the molecular dynamics simulation-derived coupling factor track each other. So it looks good, right? Then, somewhat busy slide, but let me just try to tell you what this is about. Computed survival time of water near the sphere, hydrogen bond lifetime that can be computed, or velocity autocorrelation function, or the rotational translational autocorrelation function. Obviously, that's the dynamic part, or directly computed over Hauser DNP. So the student Dennis Robinson of the advisor Scott Shell, they actually went in and calculated from the molecular dynamics also directly the relaxivity. I showed you, right? I showed the spectral density function so that you see how they did it. So the correlation is amazing. Everything correlates, meaning Overhauser DNP with dynamics and hydrogen bond lifetime survival all correlates. And also, next slide, I think should be structure. Structure, where's structure? Yeah, structure. So structure meaning tetrahedrality. So my colleagues can measure three body angle distribution, which at 104 then would be ice, and 70 is icosahedral, and bulk water is a mixture. So you can measure that as a function of glycerol concentration. The more glycerol you add, the more tetrahedral the water will become, and Overhauser DNP diffusion scales. And I can even tell you that thermodynamic property scales with coupling factor, right? Here. The entropy part of the solvation water correlates beautifully, R squared 0.99, with the coupling factor. So it sounds like we got it all. Thermodynamic structure. But on the one hand, Overhauser DNP surprisingly works well. Why does it actually work? It works really well because the water is a much stronger structure than you think. And therefore, the probe has a much less of an impact than one would naturally think. That's why. But anyhow, even when we get to structure, there is even more. When we take glycerol, there are two kinds of water besides bulk water. Okay, there's water that directly hydrogen bonds. And then there's a water that doesn't quite fit. They can't hydrogen bond, but the bulk water doesn't fit to the structure. So it forms this wrap, the clathrate-like structure. In other words, this clathrate-like structure is everywhere. Doesn't matter, PEG, DMSO, glycerol, it's all there. And so you see here, so I'm going to highlight, I think you got the point, you got all the details and why I claim structure. But finally, let me show you Overhauser-derived diffusivity and p-tet, which is probability of tetrahedrality, beautifully correlates for glycerol and for DMSO. So Overhauser DNP really tracks structure. So what's the problem? Well, what I mean by problem is that there's really a lot of unresolved question. Look at the K sigma. I didn't show it right because the ODNP and the computed one don't quite fit. Why is that? We can only hypothesize. Dennis tried everything. So this is state-of-the-art molecular dynamics, which is like femtosecond time frame changes, the best water model that they have, everything. Most likely, the problem is when you talk about picosecond dynamics, we are talking about being sensitive to hydrogen bond strengths and lengths. And I even told you water dynamic is sensitive to structure like tetrahedrality. So near any protein surface, water's hydrogen bond lengths will be different from bulk water, and that's not accounted for in the classical MD. So our best guess is that indeed some sort of quantum mechanical property must be considered. DFT for something like that is impossible, but there are models that are sort of this QMM model, or there is this model from Francesco Pesani, MB Pol, that takes this hydrogen bond variation into account. So I think that kind of work needs to be done, and there's still a lot of open question. And I hope, okay, I think I'll stop right here. I hope I made it clear where the excitement is, but also where the challenges are. And sorry for going more over time than I was intending.
That's all right. We still appreciated it. With that being said, thank you, Songi, for the great talk. I really appreciate it, especially the introduction of how actually you can measure the clustering of water, the structuring of water around your radical in that case. And more interesting, actually, like how it forms the structure, I suppose. What's a obvious point, more of a challenge now, which is still more to do. With that being said, I think it will be more interesting to look forward to the question and answer session. So with that being said, does anybody have questions right now? So if you do, please speak up right away or raise your hand, or I can also read your question if that is the case.
Don't be shy.
That's right. While we're waiting for them to figure out about their question, Songi, I have a question. With the glycerol, the last remains what you actually presented. Now you're saying that obviously glycerol structure allows for hydrogen bonding in the water network, and that's what causing the first shell of hydration, if you want to call it. Now, then also when you have two glycerols come together, water could actually form a bridge between two glycerol molecules if you go high enough in glycerol concentration.
Absolutely.
What is the highest glycerol concentration you went to?
Oh, 0 to 100 all the way. But I'm going to show you something different because it's actually, I wanted to explain, is important. The intricacy we saw is inherent to any solute, and the clustering will make things even more complicated. But it's complicated enough if you have an isotropic solution. So let's, for now, assume there is no clustering, okay? So I'm going to show DMSO is a little easier to explain because it's more dramatic. In glycerol, I need to show the structure to make the case. So if you take DMSO, it's one of those solvents where you can go from 0 to 100. So we did the experiment, and that paper is also, I think, submitted. So we did Thomas Weber, and I should have said that. Sorry, Tom, if you're there, I didn't acknowledge you. Thomas Weber did all the work. So DMSO is completely miscible, right? So you now see the sulfoxide, which is a pretty strong hydrogen bond acceptor. It's pretty negative and pretty positive here. right? So you can here very easily see that you have direct hydrogen bonding water to the oxygen, right? So you will have certainly a population that will directly hydrogen bond to the sulfoxide in some shape and form. And that population will follow a different dynamics and different structure because it's dictated by basically a partial charge electrostatic interaction, right? But what about the methyl group? What dictates the interaction there? Water cannot directly hydrogen bond to the methyl group. So it has no choice but to basically form a cage around it. And that is among the computational community very well known. Anything that's less than a nanometer, as long as there's something that water can grab onto, water will form a cage around it, right? So the sulfoxide is an extreme case because it's very obvious to all of us, methyl group cannot direct hydrogen bond, and why we should have two populations, basically bound water, wrapped water, and your bulk water, which has its typical structure, right? So now, if I add more and more DMSO, eventually I run out of water, right? So which water do you think I will run out first? So if I have a competition and there is only so much water, not enough water to hydrate everything, which one will give first?
Probably whatever can be. Well, probably the first the shell will disappear because you're gonna have.
Yeah, but even if you got rid of the first shell, now you're left with just like say 10 water.
Yeah, so the remains will be the ones bound to the oxygen. So you would form an oxygen bond.
If you eventually run out of water, eventually the clot rail will break first.
So how many hydrogen can you really bond to that oxygen? Like how many waters can you really orient with the oxygen there? Like
it's mostly one at a time, but you have many.
I thought it was two. Are you sure?
Well, it could be right. We did that. It's actually two. You're right. 1 to 2. You're right. I did that. We did that long time ago. 1 to 2. But then also remember it's statistics, right? Lots of DMSO, and then there's also indirect effect because this water is a little different from the rest of the water. So there's gonna be partial charges of this water is different from the next water. So there is also indirect interaction.
Right.
But you will run out of this water first. So this is a very obvious case. So now what has that anything to do with glycerol? Well, any solute does that because if you have glycerol, I'm drawing it wrong, so I'm sorry. You have OH. I should know this, right? Somewhere here, very hydroxyl is 3 or okay. So it's very hydrophilic. So, but there will be a conformation of glycerol where everything is hydrogen bonded and there's just no hydroxyl left, and yet there's a gap and bulk water doesn't fit. So it will still form wrap water, not as extreme as DMSO, but it will. So this wrap and bound exists no matter what solute it is. You take PEG, you think PEG is so soluble. No, PEG has plenty tetrahedral water. There's nothing that doesn't have this. Ions, maybe, I don't know. Maybe ions only have bound water. That's a different story. So I don't know whether I answered your question, but I hope I've given you that this phenomenon is general.
I mean, what I'm getting to eventually is the point. So obviously you have shown now here with glycerol and DMSO, and I think I really appreciate that because that really shows like how you have the network forming. Now, if I know, obviously, I'm a one-trick pony, I do biomolecular, and that's all what I know, really. I'm not going to pretend otherwise. Now, what I'm getting to the point is now, if I now translate what you're saying to something biomolecular, then I would think right away on like condensates, like protein condensates, the new king in the field, where people still struggling. Is it the protein seeker? Is it the protein that drives the condensates? Now, one idea would be that, well, actually it's water that drives the condensates, where you have actually the hydration shells and all that stuff removing. Now, how do they cluster together though? Like, how do they actually form? Now, in your case scenario, that's where I'm trying to get to. It would be interesting that actually that water forms that bonding, because all of it is unstructured in there. Now, how does it form any structure? Well, it does form structure, maybe through hydrogen bonding networks, not really hidden what it was, but what you have shown. So that's kind
So
of
I would say we did on purpose a lot of model system because we tried protein, and I don't have it. Maybe there's a example here, but let me just show this slide. But then there isn't much on it other than how do I do this annotation and clear? Okay. But let me actually address the liquid phase separation question you asked. I really strongly believe that it's the protein that then changes the water. And of course, water is an important player because only water reacts the way it reacts to protein, but it really is the protein. So what I mean by that is, you know, liquid phase separation is a state where you could almost make anything liquid phase separate. It's a balance of multivalent, weak enough interaction, and shouldn't be too directional. There's a balance, okay? And in that, you can have all sorts of water. You could have, we have actually studied that a while ago, you could have a liquid phase separation where you have very hydrophobic interior. And so in that context, whatever is accelerated by hydrophobic effect could be accelerated. Or I can have a very hydrophilic liquid phase separation where whatever is stabilized by that is stabilized. So I think a better way of thinking about it is, let's just take a protein, and you know this work, but I'm just going to emphasize that. A while ago, we did this work with Ryan Barnes where we look at all these sites and we measure all these different dynamics, right? And we were ranking them. And what turns out that half of the sites could be just ranked by curvature, meaning just accessibility, right? But the other half was ranked by hydrophobicity, which is the ability to form these cages. So proteins have all sorts of landscape, and now liquid phase separation is these proteins now sort of hanging in a balance. I feel like anything is possible. It's a very complicated system where it's just like a state. It's almost like saying you have a gas state, there's a liquid phase, and there's a solid state. How does the liquid state look like? Well, it depends on the liquid. That's how I think about the LLPS phase, like a state.
Okay, I appreciate it.
Okay, let's make sure somebody else, maybe I can see who is there. And can I do that where I just call out people?
Oh, yeah, go ahead.
Okay.
Can I ask a question?
Yes, please.
Yeah, it's a great talk. I have one simple question, okay? By doing this overall dynamic nuclear polarization study, can we get the information about the micro viscosity of the medium?
Yes, absolutely. I think that is a great application. So in fact, I want to show you, do I have the slide? If not, it is, oh, yeah. Do you see this slide here?
Yeah.
Oh, this is plotted incorrect. Okay, yes. So we have done that with DMSO, glycerol, and a bunch of other viscosity, right? If you have a viscosity, just to test Overhauser DNP, you can just put in any nitroxide that's inert in your medium.
Yeah.
It's a beautiful measure of viscosity. That means it should also work for microviscosity as long as you control the partitioning of your probe inside the thing you want to measure, right? If you have like your probe inside and outside, you don't know the percent in and out. Then that could be a little problematic, but you need to either be sure it's inside, or you need to label your polymer. But as long as you know what percent of your probe is inside your thing where you might want to measure the microviscosity, absolutely. That's a very, very good application. And we did a little bit of that, and yeah.
Can we use that microviscosity values to understand some of the structural aspects of the proteins?
So I would say yes and no. So depends. So what I'm showing here is, even if you take something as simple as glycerol, where you think of, at least I thought it that way too, you take glycerol and you think of the first hydration shell as one thing. And we are learning now that there are two things, right? There is, even in that first hydration shell, we have, where is my cartoon? We have wrapped water and bound water, okay? I think I can just leave it here. Wrapped water and bound water, right? It depends. I think, yeah, I mean, you can, but yes, you can, but the microviscosity will still cover the entire volume of that small container, and you will learn something about the population of that water. But the advantage is, unlike in bulk water, where you have to deal with all population, you would be confining yourself to your microvolume. Actually, I'm reminded John Frank does nice work on reverse micelle. So he puts the probe inside the reverse micelle and gets the property just from inside and learns a lot about it. So, but in that container, you still have heterogeneities. I guess that's what I'm saying.
Yeah, thanks. I think, see, probably like, when nowadays they are making a lot of different kinds of antibody solutions.
Mm-hmm.
So this, when they hope for higher concentration of antibody solutions, okay, the viscosity is the big problem for them.
Mm.
So can we use this Overgasser dynamic nuclear polarization study to do something with high concentration of antibody solutions?
I think that's a great idea. That is so Overhauser DNP at Expand, once you establish that, and currently at least Bridge 12 is offering a full solution. I'm not getting paid, so I'm just helping my friends. There's even a commercial solution, but yeah, I mean, I think in some sense I will say something that I don't know whether everyone will like it, but in any application, in any field, you need a killer application, right?
Yeah.
Overhauser DNP works really well, but I wouldn't say it found a killer application yet. What you're proposing might be, and what I define by killer application is not enough if I'm excited. It's not enough if the community is excited. People need to use it. People need to want it so much because it will solve a problem. They will need to buy it and measure, and it has to contribute, right? So sure, I mean, that would be, you should actually contact me and I will make connection for you to those who can do the testing, right? It'd be amazing. Yeah. If that could be a solution.
Thanks. If there is a time, I have one more simple question, okay?
Mm-hmm.
So for this year, Nobel Prize for Physics given to attosecond pulses.
Mm-hmm.
Is there a way, will it be kind of the attosecond pulses useful to this EPR community?
So first of all, in the EPR community, due to the terahertz conundrum or terahertz gap, even 1 nanosecond pulse isn't quite achieved. Mark Sherwin at UCSB is using a free electron laser, and it has, I think, what was the record now, 5 nanosecond or 3, trying to reach 1 nanosecond. I don't see anything. But I also want to make a more general commentary. At least in my world, the way I think about the system, we talked about bonds and molecules and atoms. So we are talking about chemical entities, and the dynamics that I'm at least aware of. The fastest one is in terms of rearrangement, picosecond. And then when it comes to catalysis, to the best of my knowledge, is femtosecond. So I don't think so. Not that I know, but who knows? One should always be open-minded, right?
Yeah, thank you. Thank you very much.
Mm-hmm.
Thank you very much, Murugan-san. Anybody else has another question or comments? The comments are more welcome. Please go ahead. So sorry, I have a question since we're waiting. Why not? So when again, it has to do with the glycerol, because I'm more fascinated with that. When it forms about glycerol, the water shell, the cathedral, or whatever you call it, can you measure the on and off rates of the water? Can you measure the on and off rates of like the K on, the K off of all the waters that are formed? Because you know what structure it does. You know what the goal is. Can you measure the individual
K on and K off of water to the structured water, you mean?
Yeah. So if you imagine you have obviously a bath of water around it, right? So then the bath of water is a source. So it's obviously unlimited water supply. So then it needs to be structured. So then there would be, then there would be a K on, K off where it will form, but it will also not live too long. Eventually will exchange again, right? I mean, that's just obvious.
So I would say for that, we need some level of spectroscopic resolution. So that's why, and I underestimated how long it would take me to explain everything. That's why I'm so gung-ho about oxygen 17 NMR. So Overhauser DNP, turns out, is a really good discovery tool because I can see phenomenon and it will give me a first pass at what's going on. And Muruga-san gave a very nice example. If you already know viscosity is your limiting factor, then these are really good measurements, right? But Overhauser DNP also corroborated that even something as simple as glycerol, we have 3 population of water, 3 population. So how are you going to measure K on and K off with 3 things without having spectroscopic resolution? But there is hope. So it turns out that once you know what's going on, if you look at oxygen 17, you can see things, but only if you know. It's funny. If you're looking for something and you think, I should see this, and you do a titration, you actually see, in many cases, signatures of what we think we can attribute to RAP water. Okay? We need to use isotope-enriched water, and we need to work really hard, but it's clearly there. So I think once you have a signature like that, there's a way to do it. And of course, the way we do this experiment isn't very optimized for sensitivity right now, but yeah, I think so.
Because one could imagine that obviously the chemical shifts for the water, which are actually bound, as you have shown already, are different chemical shifts. So wouldn't that come down to some version of a CEST experiment? Just out of my head right now.
Right, but it's some version of CEST experiment, sure. But I'm saying, so oxygen 17 NMR, line width and T2 is super sensitive to viscosity, by the way. That might be another way to do it, Muruga-san, but except oxygen 17 is expensive. But the shift is sensitive to structure, but it hasn't been used much for solution studies. There is not much. There are studies, but they're compared to the crystal and oxide community that are using it a lot. It's a desert, actually.
Well, how about using like a lanthanide that we can actually orient on a magnetic field? So if you can actually orient the lanthanide in a magnetic field, so instead of using a nitroxide in this case now, then we could actually.
I said in the beginning, what would we do without nitroxide? It's a pretty optimal probe. We tried a lot of things. Gadolinium. It's too fast relaxing. It's too broad. There's too much interference with the inner shell water, for example. Gadolinium has inner shell water. We haven't found an obvious alternative to nitroxide yet. This is the best we got so far. And nitroxide is also the probe for EPR, dipolar EPR, right? But on the other hand, if you look at the, say, fluorescent community, it's also not that there are thousands. It's also kind of a handful, right? That you get lucky, you can put it in there. So yeah, I don't think that, but why not oxygen 17 with nitroxide? I think there are NMR experts doing that, but together with dynamics. I just don't think if you have, even in glycerol, we are seeing a mixture. I don't see how I can do K on and K off in a mixture of bulk, RAP, bound, and glycerol proton, right? There are too many things that I need to deconvolute.
I got you. Right. Anybody else has some good questions?
I have one. So when you measure the diffusivity of water in close proximity of a protein, how do you take into account the mobility of the radical, if there is any mobility of the radical, if there is a mobile
It's an
linker?
extremely good question. So there are a lot of approximation that goes in, but one approximation is that really we are not measuring the diffusivity actually. Overhauser DNP is sensitive to the motion the time it takes for the motion of water to zip by the field. So it's basically in a ballistic regime. Overhauser DNP isn't sensitive to how often does it bounce back and forth. It doesn't care. It cares about how fast does it go by, not right. So it's really the speed of water that matters. So we end up ballistic regime. So I should almost come up with a different word than diffusivity. It's just that the ballistic motion does correlate with diffusivity. So we are measuring basically the mutual it's affected by both motion. It's just that at 10 gigahertz, the motion of the spin label only gets me into trouble by interfering when we are in the nanosecond regime. And now we are talking about water that's moving as slow as that inside the protein. So that's actually gets us into trouble. I think when you now have a same order of magnitude of motion, now we are like in the NOE regime. Now we need to think about if this happens, and so that becomes very, very complicated unless we can measure. Maybe if one could combine with either sidechain NMR measurement or CWEP line shape, one would need to consider that very, very carefully. But we on purpose are in the regime far away from it, for now at least.
Okay, I see. Thanks.
Okay, with that being said, I think people are ready to go off to their own experiments for some time being. With that, we want to thank Songi for your great presentation and insightful discussion afterwards. And I'm pretty sure if you guys have further questions also, feel free to reach out. I'm sure Songi doesn't mind.
Please do. And I'm happy to actually share with Thomas the paper once it's published, which is a paper that we have been working on for actually 5+ years, the Overhauser DNP theory paper. So you have a YouTube, and then do you have a way of like attaching a paper later?
Actually, Thomas, why don't you take that question?
Yes, we can put the in the description. We can put the link of the paper.
I'll be very happy to add that.
Definitely.
And I on purpose shied away from going into the equations in detail because I thought that everyone can just look it up and know how to rearrange equations. But hopefully it was useful that I focused a little bit more on why and what and the pitfalls. Yeah.
That's okay. I think people appreciated that. It's very hard to follow equation on PowerPoints. Anyways, thank you very much. And I wish everybody have a wonderful and successful day. And may all your experiments fail or succeed relatively fast.
There is no such thing as a failed experiment. Do you know that?
Only if they fail fast, so you can start a new one right away.
There is no such thing as a failed experiment.
Huh? Okay.
So everyone who's busy, just go. I'm not chit-chatting, just one more chit-chat. No, don't feel obligated. I'm just going to tell Thomas and you can hang around. So I gave the ISMA talk and I had to think about, because it was a Callahan lecture, I had to think about what am I going to say, right? So I thought, in what way did Callahan influence me? And he's famous for a lot of things and he was an amazing communicator. So that's obvious. But there's one thing I thought it wasn't so obvious. So I remember I was a student and I was mad. He came by and said, "What's going on?" "Oh, I'm stressed out. Things are not working." And he asked me, "What do you mean things are not working?" He had an experiment. It's not working. Like you said, failed experiment, right? And he said, "Songi," he says, "you must respect the experiment." Must respect the experiment. Like, who are you, basically? So his point was, you are just a humble observer of, unless you did a wrong setup or unless you messed up your sample, that's a different story. But if you did everything right, or even then, the experiment is trying to tell you something and you're not listening, right? The experiment is the king. The experiment will tell you, and you need to go where the experiment guides you, and you need to respect the experiment. There is no such thing as a failed experiment. So I'm just quoting him.
Well, I mean, okay, that's true. That's true. Unless you mess up your
point. A lot of my really, really good discovery come from accidental discoveries.
That's true. I agree with that.
Just for those who are going to have failed experiments, not failed.